All right, welcome everybody. We'll get started here in just a minute. Give some people some time to settle down. I'm sure everybody's trying to get their coffee because it's the first one. I appreciate you guys being here. Today we're going to be talking about vector databases and embeddings, so hopefully this is the right topic that you're looking for. Make sure you're in the right room. If you scan that QR code, and there'll be another one at the end, that takes you to my GitHub account. So a lot of the stuff that we talk about today will be available through the GitHub account. This one just goes to my generic GitHub. The one at the end will go to the specific project, but if you guys have any questions or anything, you can filter them through there. So a little bit about who I am. I've been coming to Stir Trek for quite a long time, both as speaker, as volunteer, as attendee. So I really appreciate you guys coming today, and I want to give a shout out to the volunteers because this stuff couldn't happen without them. So I appreciate everybody, all the volunteers for helping out. I am a lead AI developer at NetJets, so I work on their flight operations department. I'm into robotics and hacking and IoT stuff. You can find my website at thejackiegleason.com. Unfortunately, Jackie Gleason was taken. So the Jackie Gleason is the website. 3D printer. I'm also a traveler. So what I try to do for this presentation is I tried to put a bunch of different pictures in there, places I've been. So you can kind of try to see if you can guess where all of them are, which is kind of fun. So first, in the idea of transparency, I noticed after I gave this talk at Code Mesh that a lot of times presentations, when they have a title with Demystified at the end, were probably ran through an AI at some point. So mine is not immune to that. So I wanted to give a shout out to Claude for helping a little bit with some of this stuff. So that's the main AI model that I've been using to put this all together. So a little bit about what we will learn today and kind of what we're going to try to go over. First, we'll look at what vectors and embeddings are. This is meant to be a presentation for people that maybe have a variety of understanding of what these topics are in the first place. So I want to start as basic as possible, get into what the definitions of those are, what they contain, that kind of thing. I want to then go into how do we use them, how do we find similar documents, how do we use them for all of the types of use cases that we have. Also, what problems are they trying to solve? Why do we use them? What are some good use cases? What are some maybe not so good use cases? And then we'll also look at what's coming next in terms of managing context within the AI and what other options are coming online. So if we're ready, what this is kind of meant to start with is kind of what we're talking about here is these are some kind of example use cases, but they all kind of revolve around trying to understand things that are similar to each other, right? So when we're talking about trying to find a different movie that somebody might like based on their existing history, things like that, a lot of that can be done with semantic similarity, which is what we will be talking about. So these are some example use cases for things that in the real world, this type of data structure can help you deal with and kind of solve. So we'll start talking about the first main topic, which is semantic similarity. This is really the definition of what we're trying to talk about when we're talking about embeddings. In particular, vectors are just a little bit more general. We'll talk about that in the next slide. But it's really a matter of trying to take the context that we have and find things that are in a similar vector space to what we're looking for, so that we can find things that relate or things that might be add additional context to the models that we're trying to use. But this will be the main important concept that we're going to go over. All right. So how does this work, right? This is a really high-level breakdown that we'll get into a little more detailed as we go through these slides. First, you can see that we'll talk a little bit about kind of the other models of this, but this is the most basic one. We'll start with some text. We'll transform that into a numeric representation of that text that embeds context, which might be a buzzword to some people, but really just means the data that the AI understands. And then from that, we will use that context to find, or that embedding, to find other pieces of context that are within a similar area of the vector space. So similar kind of topic, similar meaning, that type of thing. So one of the things I wanted to start out with, because I think it's important to kind of understand how this is going. Everything feels like it's going super quick, and that's true, especially right now. But a lot of this stuff has been kind of in the works for a pretty long time. And kind of understanding where we came from is a really good way, I think, to kind of going forward. AI is something we've seen in movies, for a long, long time. So it's not like it's new, I was looking at a few different movies that I was kind of surprised by how old the concepts were, where they were bringing in IBM machines to do AI stuff. But kind of it started off with the idea of how do we measure occurrences of words within the document in order to be able to kind of guess at what the document is really trying to talk about or to do. And that started with TDIF, which was a way to score frequency within the words. So that was kind of like the first step toward trying to look at a word and kind of break it down into, or we'll look at a document and break it down into its individual words and score those words. Eventually we got to latent semantic analysis, which was a further step in that direction. It was kind of the, in my mind, the basic start to the idea of similarity, although that was more of a side effect than the actual reason for that individual technology. But it also kind of tends to relate a lot to what we're going to see coming out in the next kind of batch of AI stuff, which we'll talk about later, which deals with the key value cache. After that, we jump ahead a little bit to Word2Vec, which was a Google product that was meant to try to predict the next word. So the idea is it was really one of the first ones to start using shallow neural networks to try to predict the neighbor word based on the word that was, or the words that were given. And then in 2019, again, another Google kind of breakthrough was BERT, which basically deals with transformers. So now instead of just embedding individual words, we could do full sentences, full documents. This became a really big turning point in terms of using it for AI purposes as well, which led us to things like what we'll talk about later in terms of RAG databases and ways to augment kind of the context limitations that you would have in a traditional model. Something kind of coming down the pipe here, and again, we'll get to a lot of this at the end, multimodal embeddings, which deal with, instead of finding text that's similar to text, you can find sound that's similar to sound and things like that, or sound that's similar to video. So we'll get to that at the end. But the important part here is to understand that although everything seems like it's going super quick, that there is still, that there is a history to this, that you can kind of almost see a trajectory if you kind of look back a little bit. So the basic nature of what we're talking about are vectors. And so the first thing we need to understand is what a vector actually is. A vector is just an ordered list, right? So it's just, it's a set of values, typically numbers, but it doesn't have to be. And what it does is it represents something measurable. So the idea is, you could use it for things like GPS coordinates, for RGB values. You could use it for different things like in AI where we talk about weights. But the important thing is when we're talking about vectors or vector databases, a vector is just an ordered list. So don't try to complicate it too much. So the idea here is that we can use these to tie context to the actual values that we're talking about. So what is an embedding? Okay, so the next step, we know what a vector is. A vector is just a ordered list, right? And then a embedding is a vector that contains embedded context to capture meaning. So the idea is that you're taking, let's say, a document and you're embedding kind of what the meaning is within that document. So it's meant to take what's in there and kind of relate it back to other things. So kind of an example of embedding that's not AI related would be something like a Dewey Decimal encoding, or something like a GPS coordinate, like we talked about earlier, where you're giving it contextual knowledge, even if it's not AI related, right? Like you're using an ordered list to represent something, and that's kind of where the embeddings come in. So here's kind of an example. We'll talk a little bit more about multimodal at the end and how that's a little bit different, but this is an example of kind of how the idea of breaking down something into a list would work, right? We could start with this image. If we're trying to break it down, we start with the left, which is the image itself. We divide it up into pixels. We create numbers for each of the pixels, and then we can use that to embed the meaning of what the image actually is. This is similar to what we do with text embedding. So this is what most people are used to, which is you basically take objects like documents, you divide them up into tokens, you run them through an embedding model, and what you receive out the other side is a set of vectors in the form of numbers similar to like what you're seeing that are the output of the embedding model, of the document being ran through the embedding model. And we'll get into that a little bit more in detail as we go. So now that we understand what embeddings are, we need to look at how they're made. There's a different, you need what's called an embedding model. And so this is different than an AI model. It's similar. We'll talk about what the similarities and the differences are. But the idea here is that there's some typical embedding models that people use. And there's reasons why you would use them, reasons why you would use other ones. So I just kind of wanted to go over a few of them here, just so that you can kind of understand what they're for. First, we look at the OpenAI models. These were typically the first ones to come out, one of the first ones of the new set to come out. And so they're typically some of the more popular ones. The Ada 2 is a older model, but it's still one of the most used embedding models that are out there. The embedding 3 small and embedding 3 large, when it talks about that there, it's really talking, and we'll get into this later, it's talking about how big that neural network is, so how much context can kind of be stored in that embedding. And then on the open source side, Qwen 3 embeddings has become extremely popular in terms of if you want to deal with some of the more non-open AI type embedding databases and or database models. And the BJ M3 is just a different type of model that deals more with like multimodal. And same thing with the Gemini embeddings. The real advantage to the Gemini embeddings is that it can, we're talking a lot here about text, and a lot of this presentation was based around text just because originally this was a 2-hour presentation, and we got into multimodal, but it was just too much for a 1-hour presentation. So, but there are advantages to using multimodal embeddings, and embedding models like Gemini are a great option for that. Also, there is a benchmark called the MTEB, or Massive Text Embedding Benchmark. and you can get to this online, and it's a good resource for looking at kind of what the performance statistics are for a lot of these embedding models, so that you can use this to help you decide what's most important to you, what sort of things you're looking for, and what kind of model you'll use. Again, similar to I don't know how many of you guys have used run your own models before, any Hugging Face stuff, but similar to the LLM models, these have parameters, which we'll get into in a little bit, and so those parameters can affect the model. So when you see like ones in here where it's like 8 billion in the llama embedded function one, that's how big that neural network is. So the bigger the neural network, the higher the latency, all of this other stuff. So you have to kind of consider those types of things when you're looking at which model to kind of select from that perspective. All right, how do we do all this? How do these get created? Well, I'm sure most people that have been interested in LLMs have learned a little bit about neural networks, so I won't spend too much time here, but I just wanted to go over it for those that maybe don't have as deep of an understanding, because a lot of this will set up for talking about how the embeddings are actually made. So the idea here is that in a neural network, text gets broken down into chunks, and they're passed through the different layers of the neural network. With each layer, they gain attention to different contextual attributes, and that helps to guide, to be able to create the learned weights, which end up at the end of the day becoming those numbers that we see in the vector at the end. As the text moves through the layers, it gathers context, right? So it's getting more and more information as it goes through the different layers of the neural network, and by the final layer, it's built all of that contextual knowledge into kind of a format that can either predict the response, or in our case, what we're talking about, which actually skips that step, is getting an embedding back to be able to query against. And the network is trained by adjusting the weights and looking at the outcome and getting to a spot where the outcome is optimized with the weight setup. So here's kind of a document to go over how the embedding process works and how it's a little different than the LLM process. So here you can see that we start off with a word. The word gets tokenized, split up, and then it gets embedded, and then from there it goes through the neural network, goes through the different layers, gets its different attention states, gets everything kind of set up, and then it gets to a final layer, and it collapses all those in a single vector, which we'll talk a little bit about TSNE in a little while, and from that you get your embedding back vector. Kind of the only difference between this and a traditional LLM that returns back a response is that the output stuff is kind of just not done. So instead of having to generate that response, you just end up with the embedding vector. So I talked about this a little bit, but it's a really important concept when it comes to using different models, both for embedding and for normal LLMs. And this is understanding dimensions and parameters. Dimensions are the size and the shape of the vectors and tensors. So this is how does the vector space look? This is used to decide, like, basically it correlates when we look at the vector, the number of numbers in the vector correlate to the dimensions within the model. The parameters are the trainable values, so it's all of the kind of biases and weights that are put into the actual model itself. You can see here that at the bottom, like what I was talking about, when we see something like, let's say, Quinn 3, 0.6 billion, we can tell that there's 600 million parameters in that. And so this is nice because, for example, that Quinn 306 billion or 500 million, whatever you want to call it, 600 million model is a really good model for running on Raspberry Pis, right? And we know that because we know it has a lot smaller weight or parameter count. So we know that it's going to be able to run in a smaller vector space. So it's going to be easier for it to run on something like a Raspberry Pi. So when you're downloading these models at home and you're using Ollama or something like that, and you see like 24 billion, and you're running on like Mac Neo or something, it might become a bit of a problem to run those models, and that's because of how big of a space it needs in order to be able to run everything. So we talked a little bit about tokenization. We'll get a little bit more into that. This is the first step in the pipeline. Basically, a token isn't necessarily always a full word. It can be a subset of that word. But the idea here is it gets broken down into subcomponents that it can then embed. It can also have what's called overlap. So you could have, like a word, and half of that is one token, the whole word is a token, and another half is a token. You can do things like that where if it helps to add context to it, you could have multiple words, split into multiple words, stuff like that. But all of these end up getting mapped, and then all of those tokens get converted into these embeddings as well. And then that's what kind of helps to capture that semantic meaning. Yeah, so they all, at the end, they'll all collapse down into a single vector. Yeah, the important takeaway here is similar embeddings end up producing similar embeddings. Similar tokens end up producing similar embeddings. So that's the idea of how it's easier to, or how it's used to kind of find similar items. All right, so the type of tokenization you do matters. The idea here is that tokenization can impact the how well the meaning is stored, because if you've made it too small, it might not be able to retain the context that's necessary. Like we talked about, context length is important. So some of the different models have different context windows and things like that. So that can affect what type of tokenization you use, and also cost and performance can come into play there as well. So we're going to try to get in a little bit to the mathy part of it. So we'll go from there. So now we're going to talk about semantic similarity. The next question is how do we actually measure how close two embeddings are to each other? You've got three main options, or these are vectors, rather, two vectors close to each other. You've got Euclidean distance, you've got dot product, and you've got cosine similarity. Each of these kind of measure a different aspect of where the embedding is in terms of the vector space. In terms of the Euclidean distance, it is the most intuitive. It's literally the straight line between two points in space. It's like measuring the distance on a map. The shorter the distance, the more similar the two embeddings are. It's the easiest to reason about. It's sensitive to magnitude, meaning a really long document can appear further away from a short one, even if they are about the same topic. So that's the important part to remember about Euclidean distance. Cosine similarity fixes that problem by ignoring magnitude entirely and just measuring the angle between two vectors. Two vectors pointing in the same direction score a highly similar regardless of how long they are. This is why cosine similarity is commonly used in natural language processing. It measures similarity regardless of magnitude. So a document where the word fruit appears 30 times and one where it appears 10 times can still be recognized as similar. Dot product is a kind of hybrid between the two. It factors both direction and magnitude. It's useful for when magnitude carries meaning in your application, like user activity levels in a recommendation system, or when your embedding model was specifically trained using dot product loss, which is a specific type of training. So those are kind of the different ways that we can look at measuring semantic similarity. Here's just kind of a breakdown of how that works. So you can see here that most of these are from either, so you can see cosine similarity is -1 to 1, Euclidean distance is 0 to infinity, and dot product is -infinity to infinity. That kind of breaks down kind of how those are kind of measured from that perspective. So dimensional space, we talked a little bit about dimensions before, right? So we'll go into kind of, here we'll go into kind of what that means. So you can kind of break it down as like one dimension kind of deals with one topic, whereas when we start to increase the dimension, we start to increase the amount of topics that we can talk about in it. So the more concepts we have, the better our contextual information will be, and the more information we will be able to use within our embedding. So this is a very so a lot of what we've been talking about is how we translate it, and then one thing that we're going to lose a little bit on here because of the time is something called TS&E, which is kind of where you take a high dimensional vector, and you project it down into a few different dimensions. So it can take extremely large amounts of context or large amounts of factors and kind of distill them down into kind of almost like a two-dimensional or n-dimensional graph, depending on how you want to set them up. So one of the easiest way to do it is in a two-dimensional graph, where or like four-dimensional, depending on what you're doing. But two-dimensional graph where it kind of shows you like the relationship between the terms. So in this one, the idea is this is an older problem. And here, the idea is if you have a king, you subtract man, and you add woman in the vector space, you should end up as near queen. And the idea here is that that's because of the context it's used to train on, all of that kind of stuff. It embeds that into the embedding model that it's using. And so when it projects out into the vector space, you'll actually end up seeing that this comes out in real life, that when you take these topics and you use them just like their normal, subtract one vector from another vector type numbers, you end up in the same vector space as what you're looking for. And that's kind of the crux of what embeddings used for in order in terms of finding other data that's similar. So to review, we talked about what an embedding is. We talked a little bit about dimensions and shape and similarity, right? So dimensions are what are the different contexts that's available. Similarity is how similar is it. Shape is kind of what does the vector space look like, right? So how do we use embeddings? We looked at how do we tokenize things, how do we use semantic similarity, and what are embedding models and how do we use them? So now we'll talk a little bit about, now that we understand all that, now we understand kind of what embeddings are, what they're used for, we can talk about kind of how we store them. And typically with this stuff, you'll use what's called a vector store. And now that we know what vectors are, we can tell kind of what a vector store is. It's a key value kind of store where the key is your embedding and the value is the value that was used to create the embedding, right? So it makes it so that you can search based on the embedding, which is where you get the idea of similarity searches. So it stores, like I said, it stores the embedding as well as the document that was used to create it. It's deterministic, so it should be repeatable. There's other things that you can add to it. So once you get something that's in a certain spot in vector space that's close to what you're looking for, you can look at neighbors to that in different ways. So you can look at other documents that might be related to that in terms of, we'll talk a little bit about graph, Neo4j and some of the graph database stuff that they've got going on with that stuff. And vector spaces can be multimodal, right? Because we've broken it down. And multimodal just means not just text, right? So I know I've said that a couple times. Some people might not know what that means. That just means not just text. It can be images, everything like that. But vector spaces, because we've already broke it down into numbers, can, what it's an embedding doesn't matter. It can be anything. And again, so like this kind of just goes to show kind of an example of like how it could be used to deal with that. So we have what's called retrieval augmented generation. The idea here is that you generate these embeddings, and like I said, you store them in a persistence store that that contains or that stores the embedding and then also stores the document. Then what you do is you go through and you submit a similar, or like your prompt, let's say, and you would embed that prompt, and then you would use that embedding to search for similar embeddings, right? So now that you have the embedding of your prompt, you have the contextual information about your prompt. You can then go back through and search for different documents and things like that that are related to your prompt. With RAGs, there's a bunch of different types of RAGs. So a lot of them will allow you to do use metadata and things like that on top of it. This is pretty important because, for example, if you're trying to ingest an entire documentation library or like some kind of big, like your Confluence site or your SharePoint site at work, a lot of that data might be out of date, right? And when you think about something like a RAG, it's just going to look at the similarity of the documents, right? It's not going to consider how old or new the document is. It's not going to consider how good a quality the answer is, how authoritative the source is, right? It's just going to go ahead and try to find the thing that's closest to what you're looking for. So that's where things like, some of the more advanced RAG systems come into place. I don't know if anybody's used any of the, like, in the AWS world, they have like 3 different vector stores now, right? They have OpenSearch, they have S3 vector store, and they have Neptune, right? And all of them have different advantages, right? OpenSearch is for ANN and search-based stuff. Neptune is for graphs, and S3 is just for simple embeddings, right? So there's a lot of differentiation in this market. So RAG isn't just like kind of a, it's a little bit more nuanced than just RAGs or RAGs is what I'm trying to get at. The idea with a RAG, though, the main point of it is that most models, and this is starting to change a little bit, and we'll talk about this a little later, have a very limited context window. So the idea is you can only put so much into your prompt before you'll overflow your context window. I'm sure we've all been there. We've been using Claude Code, and it gives us the message where it can't go any further unless we compact, and then it may or may not compact, depending on how close we are to that limit. So that's kind of where that comes into play. Now, instead of having to embed a whole bunch of documents, instead of having to like have the AI go out to a web browser, search the documentation in the web browser, get all of that data added to the context, we can instead have a pre-processing step where we embed that data, we add it to the RAG database, and now we can pull in just the parts of that data that we need without having to have the entire website and everything else within our context. So what it does is it provides you the ability to take a smaller context window and kind of expand it to some extent because you can filter out things that don't matter. So we talked about this a little bit. These are some of the options that we have for vector storage. There's, of course, the vector native databases, which are the first ones to come out. And that's ones like Pinecone. Like I talked about just a little bit ago, we have cloud native ones. There's in-memory ones, right? So LangChain.js, Redis, all of those have in-memory stores that are available. Document databases such as MongoDB, Atlas Vector Search. Graph databases, like I said, all of these just have different reasons to use them. And then the next generation is going to be called hypergraph, where it deals with a lot more complex relationships within the graph and tries to preserve some more contextual information to allow for even more advanced searches than just going to a node and looking for all of the other nodes around it. Probably one of the best ones to use if you're just starting out is PG Vector. And this is because I'm sure most people in this room have used Postgres before. And so PG Vector is their version of the RAG database. It runs on Postgres, like it sounds. And it allows you to do normal vector searching as well as some advanced options. Like all these are nearest neighbor options. So just ways to kind of add additional context without having to, pull everything in the world in. It allows you to do some more complex similarity searches. And it's supported on all of the different cloud providers, which is nice, and it's highly scalable. So probably if you're going to start playing with this in your personal projects and you don't have like an AWS account or something like that, the RAG databases like Pinecone, they do have a free tier, so you could play with those. But if you're the kind of person that wants to run your own database and all that while you're playing with this stuff, then PG Vector is a very good option for that. All right, so I wanted to do a little demo because we've talked a lot about this, and it's I'm sure I've tried to be repetitive, so I'm sure some of it's stuck, some of it might not have stuck as well. So I wanted to kind of walk through an example project. And again, this example project is available on my GitHub that I mentioned earlier. I have it running locally, so it may be a little latent. There may be a little bit of latency here because I was worried about the whole Wi-Fi situation within the theaters. So this is all run locally. There's no cloud information or anything in this to have to deal with. But the idea here is the first step, just to be able to see kind of how the vector embedding works. We can put in like a sentence like, hello, welcome. Oh, I'm not at code mesh. And then hopefully live demo, so and all that. We'll see it come back, and you can see here where it talks about the dimensions, and those are based on the model that we used, right? And you can see here that what it comes back as, we have just like, kind of the first 10 to kind of visualize that it's just a bunch of numbers between -1 and 1, right? And so that's where we can see like the numbers that we see here. You see here that you see all of the numbers in the embedding in the entire vector, right? And so this is what I mean by, for that sentence, it took this sentence and it breaks it down into an embedding that looks like this. So that's what we mean when we say that like it's getting embedded. It's taking that data, running it through the model, and coming back with a vector embedding that looks similar to like what we're seeing. So with that, what we can do is what I've done in here is I've created a simple in-memory vector store that allows us to store information. So the first thing we can do is we can come in here and we can add prompts, right? So we can say like, well, here, before we do this, I'm going to do this. So like, let's say we're talking about the car, right? If we go over to the RAG chat, which we have right now, and we ask it like, what color is the car? It should, if it's working right, say that it doesn't have any information about that. I can't tell you what color the car is because there's no context to tell me what color the car is, right? Because we have no context in there at all. And so that's kind of where we're at. So what we can do is we can go into here. And so before we get into the LLM model, this isn't even with the LLM model. This is just with the searching and the querying that's available within the RAG store itself. We can go in here and we can say something like, the car is green. And we'll say like the B is yellow. And we can say stuff like the, and I'm just doing this for simplicity purposes, right? Like you can do whatever you want here. Right? And then what you can do is you can search. And typically when you search a RAG database or any kind of similarity search, what you provide is you provide the number of results that you want back. This is because it's going to give you n number of results that are as close to what you put in there as possible. So in this case, we'll go ahead and just do one. And we can say, so as you can see here, remember, this is the text that we put in there, right? So it's not telling me that the car is green. We just put the text in there that says the car is green. And so we got, so because it gives us a score, we can see how close that score was to what we were looking for. So this will have the highest score. If we say like 2 here, oops, not 52, well maybe. Got a bug, somebody put that on GitHub. You can see here if we put 2, we have 2 different results. One of them is 0.6 and one of them is 0.5. So it gets a little bit higher depending on how close it is to what it's going to. And this is what they call the score or the temperature. So in this RAG chat, as you can see, I'm running a little bit low on time, but we can play with the temperature to show what kind of temperature we'd accept. We can show how many documents we want to retrieve, right? So we can do that, and then what we can do is if we say like, now, because it has the context that's available to it, it can now tell us what color the car is, right? So all of that, real quick, because we're running low on time, I'm just going to zoom through this. RAG is dead. This is something that people have been saying because context windows are getting larger. So people kind of wonder, why do I need a RAG database if context windows are getting larger? This is kind of a misnomer. I think it's not a very good idea because context window, you're going to get more and more data that you're feeding into this. Eventually context windows will become an issue again. You might want to use a smaller model to avoid latency, things like that. All of those are good reasons to use RAG, but there are a lot of other options coming through the pipe. One of them that you want to look at is CAG, which deals with the key value store. This is typically used for things that are a little bit more static, so they're not changing. In a RAG, you can change the data, change the embedding, and remove the old embedding. This is more for actually injecting the context into the key value cache for the model, so it's part of the actual neural network that happens. And that's where some of the turboquant stuff can come into play as well. CAG versus RAG, just like I said, easier to update, unlimited storage, static data, and it's limited to the context window of the actual model itself. Multimodal we talked about. This is some cool stuff, even up to the point where you can embed brain data and store it and try to like inference thought data between two different people, which is interesting and a whole really cool part of embedding that's coming out right now. You can imagine it almost being like thinking about it and the AI figuring out how to make it happen kind of thing. It's actually kind of cool. And finally, another term to kind of think about is fine-tuning. Fine-tuning is not really dealing with embeddings. It's more going back and actually training the model. But in some cases, that might be the better option. So just make sure that you kind of think about what you're using it for and kind of put in that consideration as well to make sure. Yeah, so I think, and that should be the QR code to actually get to the site itself. Do we have time for questions? Am I? 1 minute. 1 minute, okay. So I guess we don't have time for questions. I thought it was another 5 minutes, so I apologize. But if you want, you can meet with me after, and I'll be more than happy to answer any questions for you. Sorry again about being a little too close to the wire on that. But I really appreciate you guys coming out tonight, or out today. I guess it's still 9:30. But, like I said, I'll be up here for questions if you have any.